Good morning, everyone. Test today? No test, just disinterest. That's fine. I think a few are scrambling in towards the end there. So we're pretty much halfway through the term. I know it's difficult to believe it, but we are lecture 19 today. Basically, by the time we're halfway through, we'll be at the halfway point for the content in this class. And even though we're halfway through the course, we're still talking about tension members. We're pivoting a little bit though, because we spent quite a bit of time talking about bolted tension members. We would drill holes in the member itself to bolt the member to the gusset plate to make a connection. And when we did that, we removed some cross-sectional area and introduced some potential failure modes like net section fracture and block shear failure. Welding's not really going to change too much for us. We're still going to have to consider a net section, which might seem weird because we're not removing material, and we're still going to have to consider these other failure limit states. But before we can talk about how welds influence the strength of the members, we actually have to talk about the strength of the welds themselves. So I'm going a little bit backwards compared to what we did for bolted tension members. For bolted tension members, we talked about the strength of the member, then we talked about the strength of the bolts. Today I'm going to start talking about the strength of the welds, and we'll see in the next two lectures, maybe one, I can't remember exactly, how the welds and the weld arrangement influences the strength of the tension member at the welded connection. So last day I introduced welding in general. Today we're going to talk about fillet welds. They're the most common weld that we're going to be using, generally speaking, in structural engineering applications. As I mentioned, groove welds have their place, but 80% of welds tend to be fillet welds. They're the simplest to do, and the nice part is that their calculations are usually pretty straightforward as well. I do want to just come back to this example because I had alluded to it before, that in this particular building, the braces were bolted at one end, and due to the mechanism that they were employing, or the procedure they were using to take the slack out of the brace with a pre-tensioning method, they bolted one side, pre-tensioned the brace, and while it had a tension on it, they welded the member at the other end to the gusset plate. So at the upper side, we had a connection that looked something like this, and down here in the middle, we had connections that look something like this. And here you can actually see, just at the bottom here, this is where that angle clip was, and that's where the weld that they had to grind away was. They had pre-tensioned everything here. And it's pretty clear to me, anyway, that you can see there are at least two beads of weld here. Okay, so oftentimes, or generally, we can only build up a certain amount of weld by running the electrode in a single pass. A lot of times it's going to take multiple passes to build up a weld that's big enough for us to have enough resistance through that weld metal that we can transfer the tension force to the gusset plate. I guess what I'll say very briefly about this one is basically when the tension gets applied to the structure or to this member acting as a brace in the building, basically those stresses transfer down through and into the welds. And so in this case, the welds are going to be sharing half the load that's applied to the brace in this case, or we could consider the total length of weld as being equal to this length plus this length. And so here for us, the total length of weld that we have would be the 2 times that L value. When it comes to ultimate limit states, we're going to focus on two in particular today, and that's fillet welds in direct shear and fillet welds in direct tension. And we're going to see that fillet welds can be in something other than direct shear or tension. They can be anywhere in between. And the strength of the weld we're going to see is proportional to the size, of course. That makes sense. Everything else so far has had a strength proportional to the size. We'll talk about what this effective area of the weld is. We talked a little bit already about what this XU term is. XU is the ultimate strength of the weld metal, and that's denoted through the E49XX specification we might state for the welds, and that tells us that, in this case, XU would be 490 MPa. Okay, so we're going to look at what it means to just take 0.67 VAW XU, what it means to take VAW XU, how sometimes the strength is somewhere in between these two terms, and we'll talk about calculating the effective area for the welds. Basically, after this morning, you should be able to determine maximum and minimum fillet weld size requirements. We're going to see that when we're welding plates, especially the thicker they get, we have to put at least a a minimum amount of weld in place just to generate enough heat for the weld to be competent. And from a quality control and inspection perspective, from time to time there will be maximum weld sizes to employ as well. You should be able to calculate the strength of fillet weld segments, connecting a tension member to a competent gusset plate, and consider the influence of different weld orientations on the strength of the different fillet weld segments that are connecting the tension member to the gusset plate. Does anyone have any questions about why these three things might be important before we get into the material this morning? Okay, I finally got pull everywhere under control here. This might seem like a silly question, but it is an important one. I'm showing a right angle triangle here where A is equal to D. Which of these colored lines in this triangle is the shortest line? I hope that even my 6-year-old son could perhaps answer this question, but it is important, and we'll see why in a minute. Again, I should have the counter on this damn thing to see how many people are actually answering. So I don't think there's a whole lot of confusion here. Of course, when we're looking at a right angle triangle like this, the minimum distance between what's going to be here, in this case, the free face of the weld. This is going to be the face of the weld that's not fused to anything. It's just open. And the corner where the two fused faces intersect, of course, is going to be C, right? Basically, what I'm going to be getting at here is the strength of the welds in terms of where the stresses are the highest. The stresses are going to be the highest where the area is the smallest. And for us, the effective area for our fillet welds is going to be through the line that's shortest, through the corner of the weld, into the free face of the weld. And what I mean by that is when we have a fillet weld, we have the face of the weld, which is not fused to anything. It's just what you can see from looking at the weld. And then we have the fused faces, right? So when you're depositing the weld metal, it's molten. It's going to melt the steel that it's connecting to. And as it solidifies, it's going to fuse the weld metal and the steel together at these two locations. So these two fused faces, they're connected to the weld. Here, where the two metal pieces are connected, there is no fusion between those two faces. That's just where the two pieces of steel butt up against each other. And so the only two faces that are actually making this connection are the face on the stem of the connection here and the face on the other part of the connection here. There's some other things that are important to cover here. The corner is called the root of the weld. That's where you tend to get some stress concentrations, and it's important to have adequate penetration into that spot so that we don't have any kind of fatigue cracking going on in those locations. And then there's something that we call the HAZ, or the heat affected zone. And the heat affected zone is basically a spot where the weld metal, or the metal that's being fused, hasn't been molten necessarily, so it hasn't melted, but it's come very close to being molten, and so there's a heat that's affecting that area. That's where we tend to get failure through the base metal, because it tends to heat up and might be a little bit softer or weaker through that area. Generally speaking, though, as long as we're using matching electrodes, which means for 300W and 350W steel, the matching electrode is E49XX, we generally don't have to worry about the strength of the base metal through that heat affected zone. The leg length is called D, and that's literally just the length of this line and this line. And generally speaking, fillet welds, when you're making one, these two legs are supposed to be the same length. And so when we call out the size of a fillet weld, it's based on the leg length. They should always be equal, and we call that leg length D. When we're looking at the potential failure of these welds, as I'll show you in a minute, we're going to be focusing on what we call the effective throat of the weld. And the effective throat is basically, like we had on the pull everywhere thing here, it's basically dimension C. And that's the dimension from the root of the weld out to the face perpendicularly. That's the shortest distance. And we're going to see, as the stress gets transferred from this leg of the weld to this leg of the weld, those stresses have to pass through in shear or tension through the location where the stresses are going to be the highest. When we're making these welds, there are some things to consider, and this is important if you're the engineer of record specifying things or if you're the engineer for the fabricator. If you're doing welding in the shop, you're in a very well-controlled environment, and so you can make a weld with a single pass of the electrode so that D is equal to 8 millimeters. That's the maximum weld size that you could generate in the shop. And if you're in the field, this is something to be very careful about, is you're not actually allowed to generate a field weld that's bigger than just field conditions, the position, the fact that there are environmental considerations. It's generally more difficult to control the quality of those welds, and so we're not allowed to make D bigger than 6 in a single pass. If you want to make D 8 or 10 or 12, and you're in the field, that means you're going to have to build up weld metal using several passes, and I'll show you what that looks like here in a minute. If I was to put a real cross-section of what that weld might look like, an image of somebody having done a weld and having cut through it and looking at what that surface looks like through some kind of microscope, you can see that the weld metal, as it materializes, of course there's some magnetic field that basically controls how it solidifies, but you can see the affected zone here quite clearly, and you can see how deep the root of the weld is penetrated there into these pieces of steel that are being fused together. Does anyone have any questions about fillet weld anatomy before we continue on this morning? Katie?
What did you say that shortest path is called?
That's the throat. We call that the effective throat. That's here. And actually, that's a good thing I might ask before we continue on. If we have a leg size D that we're specifying, maybe it's 8, maybe it's 6, maybe it's whatever, and we're calculating the throat length here, maybe even coming back to this rectangle, basically we're specifying A, which is equal to D, and it's a right angle triangle. How do we calculate C? Does anyone remember? Well, we've got basically, I can't draw it there, but we've got a 45-degree angle, and so we can say, well, the throat, the effective throat, I'll just call it, I don't know, E for no other. It's going to be equal to D sine 45, right? And you're going to see me just always write as root 2, just using the special triangles. We'll see how that plays out in a second. But the effective throat is that minimum distance C from the pull everywhere slide, and that's calculated as the leg size D divided by the square root of 2. Anything else? In terms of actual maximum and minimum sizes, there's, of course, maximum single pass that you can physically do or do with a minimum amount of quality. But in terms of the actual maximum size you can build up or the minimum size required, it depends on the thickness of the steel that we're dealing with. And so here, that's why I was going to bring that, anyway, I was going to bring that steel back, and I thought, oh, you already had it in your hands like 3 times this term. But for the minimum single pass, if you're using like a small plate, you can use a single pass as small as 3 millimeters. If you're dealing with something between 1/2 inch and 3/4, which is 12 and 20 millimeters, you can do 6, which is about as soon as your plate gets thick enough, basically exceeding 3/4 of an inch, you have to use a minimum weld size of 8 millimeters. And the reason for that is when the steel is really thick, you're putting heat into the plate, and the steel is just going to take that heat and disperse it out throughout the cross-section of the steel, and it's not going to be in place long enough at the weld to have an effective fusion. And so the bigger the weld size, the more heat you're putting into that weld, and so the thicker the plate steel, the more heat you have to put, and that's why the minimum weld size for really thick steel is 8 millimeters. Now that's going to cause some headaches from time to time. That's basically saying, well, I'm limited to 6 millimeters in the field, and so if I have 20 millimeter thick steel, I'm not really going to be able to do that in the field, right? So I have to be quite careful about what kind of thicknesses I'm working with and when I'm going to have to do a shop weld versus a field weld, so that when I'm figuring out what I have to do, I know that I'm not going to be telling the crew in the field to start welding 20 millimeter plate together when they can only do 6 millimeter welds in a single pass. Maximum fillet weld sizes only apply at edges of plates. Otherwise, there is no maximum fillet weld size that you can generate. What I mean by that is, in this situation, there is no real maximum fillet weld size. You can make D as big as you want. You can make it this big, And basically you can just make it as big, of course, as the steel is that you have to connect it. So practically speaking, I can't exceed the boundaries of the steel here. And that's basically what this other maximum fillet weld size at plate edges is getting to. For example, if you're doing a lap splice, which means you're taking two pieces of plate, something like this, and you're trying to do a fillet weld here, for certain sizes of plates, if you exceed 6 millimeters, you're not allowed to cover any more of a gap than leaving 2 millimeters at the edge of that plate. If you have a piece of plate that's 6 millimeters or thinner, you can go right to the edge. The reason you have this size, though, is because if you start to burn into the edge here, it's actually quite possible that instead of making a fillet weld that looks like this, that you burn away the edge of the plate, that melts away, and you have a fillet weld that looks something like this. It looks like it's a good weld because you see size D and size D, but because you've melted away some of the plate, you're not actually getting the entire effective throw depth that you think you're getting. And so from an inspection point of view, it's very hard to tell whether or not the fillet weld is a quality weld or not, because you're not getting the full penetration. And so that's why we leave at least 2 millimeters at that edge so that this person who's inspecting the weld can see it. And so when we're dealing with lap splices or welding the edges of plates together, we usually have to leave at least 2 millimeters here of thickness left after we complete the fillet weld. Okay, the last thing I'll say about that before we get into the strength of welds, as I mentioned before, if we need to make bigger welds, we can only make a certain size weld in a single pass, 6 millimeters in the field, 8 millimeters if we're doing it in the shop. And if you want to make bigger welds, you have to build them up. And so this is a nice picture showing the first 3, perhaps, lines of weld that they might have used to make something. If they want to make 10, they have to do another 4 passes. 12, they have to do another 6 passes. 16, they have to do another 10 passes, right? So building up a significant amount of fillet weld to increase your size takes a lot of time and a lot of effort. So for example here, 8, that's not a good color, 8 millimeters might require, let's just say 3 passes, and then maybe 10 millimeters is going to require 3 plus 4, which is 7 passes. And then we've got 12 millimeter, which might be plus 6, so 13 passes. To go from an 8 millimeter weld to a 12 millimeter weld, which is only to do more than 4 times the welding. So we're going to see here in a minute the strength of the weld is directly proportional to the size, and so a 12 millimeter weld is only 50% stronger than an 8 millimeter weld, but in this case, if we consider these dimensions, you need more than 4 times the amount of weld actually present there to build up 50% more strength. So for that reason, as I alluded to back here, longer, smaller welds tend to be more efficient than bigger, shorter welds because you end up with more volume when you're building up larger welds. If we think of the cross-sectional area here, the area of the weld or the volume of the weld is going to be proportional to d squared, whereas the strength is just going to be proportional to d. So that's an indicator that you should be specifying smaller welds where possible, unless it's impractical to do so. Okay, so we've talked a little bit about what fillet welds are, what the maximum and minimum fillet weld sizes might be, and how we'd build up bigger welds if we need them. Does anybody have any questions about any of this stuff before we continue on? Okay. As the engineer, we care about the strength of these welds. We need to make sure we're providing enough weld metal so that it doesn't tear apart when the tension or compression forces are going to be applied. Clause 13.3 talks about welds in general, and 13.2.2 specifically talks about fillet welds. And for the most part, we're going to see that fillet welds, when loaded in pure shear, the equation to calculate the strength is the 0.67 phi-w-aw xu term. And I'll spend a little bit of time unpacking what this means and how we calculate some of these values. So this equation applies to welds in direct shear. And basically what this means here is we've got a fused face right over here connecting one piece of steel. So that's connected to one piece. We have a fused face down here that's connected to the other piece, We're basically taking I guess I could draw the arrow the other way. We're taking force from one weld in one direction, like shown here, and transferring that through direct shear in that weld to the piece of steel on the other side. And so the force is coming from the piece of steel fused by this face, going to the piece of steel fused through this face, transferred through a shear along the length of this weld. Basically what happens when that weld starts to fill is the stresses will be maximum on the smallest area. And as I mentioned, the smallest area is going to be through effective throat. And so here we've got a length of d over root 2. We've got the length, the face that's carrying the highest stress has an area of d over root 2 times LW. And so when we're calculating the the area for our welds in direct shear, this is the equation that we're going to be seeing most often, d over root 2 times whatever the length of our weld is going to be. The only time that's going to be different, or maybe I'll just say one thing before I say it's going to be different, if we have back here two L's, right? So we've got one fillet weld on one side, another fillet weld on the other side. Here we would just say LW is equal to 2 times whatever the length on each side is. And so we don't necessarily calculate the strength of each weld. We just say the total weld length is the two of these lengths added together. And so LW would be the length on both sides. The only time that this is going to change in terms of an expression for calculating AW is if you're developing a fillet weld for pieces where the plates of steel are not normal to each other. So if the if the angle exceeds the angle for this case here, the leg size generally stays the same, and so we're going to keep the legs the same length. The smaller the effective throat is going to be a little bit smaller as well, whereas if we're working with an angle where we have something less than 90 degrees, again, the size D is generally going to stay the same, and in that case we have a slightly bigger effective throat. Okay, so this is something to be aware of. Probably not going to see this too much in this course. I might ask you on a quiz or something to calculate the effective throat width for a certain weld orientation. But generally speaking, 95% of the time we're going to be dealing with this case up here where D over root 2 is going to give us the effective throat depth. Does anyone have any questions about how these fillet welds might fail in direct shear, why we're taking this area, or anything else before we get into the calculation of the strength of these welds? Katie? Because that's just, if we come here, we've got a force that's applied through this tension member. That force has to come through these welds, and that, by the direction of the load, loads those welds in shear. We're going to see in a minute when welds can be in tension. We'll talk about differences between shear and tension in welds. But it's just the way that the loads are getting transferred here. It's taking tension through shear welds along the length of those two welds on either side. Anything else? Okay, so for these welds in shear, we take the area that we just talked about, multiply that by strength of welds in shear, and again, we have to remember here that XU, these times of values are always based on the specified tensile strength. Right, so that's the ultimate tensile strength, and so convert that to shear, we normally multiply by 0.6. They found, generally speaking, that I don't know why, but due to the metallurgy or whatever's going on with welds and shear, 0.67 is actually a better conversion between the tensile strength of the weld strength. And so really, we're taking the area of the weld and multiplying that by 0.67 XU, which is the ultimate shear strength of the weld metal. When we're dealing with fillet welds or any kind of welds, again, we're using the same reliability factor we talked about the other day, 4.5, and that requires us to use a resistance factor 0.67. Variability in the welds tends to be more compared to other components of the steel structures we're dealing with. Does anyone have any questions about this equation or how we might use it before we move forward? We'll see it used in an example at the end, but any questions about what we talked about so far? Okay. So that's fillet welds and shear, and again, that would be a situation something like this. From time to time, there might also be welds on a face that's perpendicular to the applied load. So if welds are on the face that are parallel to the applied load, they're going to be in shear. When we have welds that are perpendicular to the applied load, those are going to be in tension. And it's possible, though not often practical, that we might have welds loaded at different orientations. Okay, so this is the strength that we get from a weld in pure shear, and we can see where we might get shear-induced stresses acting on our welds. This is a graph that shows how the force deformation response for welds changes with the angle of loading. We just talked about a case where we have welds that are parallel to the applied load. And for this case, the distance or the angle between the applied load and the axiom of the weld is 0, right, parallel. And when we have welds loaded in shear, as I mentioned in lecture 2 for this course, the failure of steel in shear is very ductile. And so we get a response something like this. We reach the ultimate strength somewhere out here, off towards a failure strain where we get fracture of the weld. Okay, so welds, when they're loaded in shear, are very ductile. If you were to change the loading angle, and the most common way you could think about that would be something like, this down here. If we had a weld along the backside of a steel plate, for example, and we're pulling on that steel plate, we're generally going to see that as the angle goes from 0 to 90 degrees, the strength is going to increase because we're failing the weld in shear anymore, we're failing the weld in tension, and the tensile stresses at failure are higher than the stresses in shear at failure. But we're also going to reduce the deformation capacity. And so we're increasing the strength by upwards of 1.5 times from whatever it is here, but we're also decreasing the ductility of that connection. For that reason, we generally want to, where possible, the weld specified so that they're loaded in pure shear, because it's more ductile. They might not be as strong, but we tend to want to enforce ductile failure mechanisms wherever possible. However, there are some times where you might not be able to always load in pure shear. The most common example would be if we were to weld the backside of this plate as well. In that case, with welds in shear and some welds in tension, the welds in tension have an ultimate strength 50% higher, significantly less compared to this shear strength that's 1.5 times lower. That's occurring at a larger strain demand. What does this look like on the welds? Well, now we're thinking about a situation where the fused face is getting pulled apart by a force acting this way, and that's transferring the stress through the weld to a force acting in the opposite direction. And basically what's going to happen there is, again, the force, or the stress, I guess should say, will be highest through the location in this weld where the area is the smallest. That's, of course, through the effective throat. For us, in this case, the area of the weld does not change. The area of weld generally doesn't change if it's loaded in shear versus if it's loaded in tension. It's simply the stress at failure on that face that changes depending on whether or not it's pure shear or in pure tension. Okay, so basically, here we've got 0.67 VW AW XU. If we multiply 0.67, which is basically, that's 2/3. If we multiply 2/3 by 1.5, what do we get? 2/3 of 1.5 is 1. Great. So up here for welds in tension, we're multiplying the 0.67 by 2/3. We get VW AW XU. And that's expected because the weld is failing in tension. It should be proportional to the cross-sectional area of the weld and to the tensile strength, right? So that makes sense. So basically we're playing within a range of 0.67 VW AW XU for welds in pure shear, VW AW XU for welds in pure tension. And if for some reason your welds are at a different orientation, we have a little curve here through the ultimate strengths of these other points. And we may want to try to account for that if we've got welds that are not loaded at either 90 or 0 degrees. What S16 tells us we can use is what a modification factor for strength for different values of theta. Basically what this is we can take our 0.67 VW AW XU and multiply it by this factor, which is calculated as 1 plus a half of sine theta to the power of 1.5. So this works for different values of theta. Let's just say if theta is equal to 0 degrees, what does this factor calculate out to be? 1 plus a half sine theta to the 1.5. If theta is 0, what should this factor be? 1, right? Sine theta is 0. Anything 0 to the power of anything 0. Multiply anything by 0 is 0. So this goes to 0 and we get 1. If we have theta is equal to 90 degrees, what does this expression give us, do you think? Sorry, what was that? 1.5, right. Because sine of 90 is 1. 1 to the power of anything is 1. Half of 1 is a half. You get 1 plus a half, which would be 1.5 for theta is 90 degrees. All right, so basically this factor is going to be something between 1 and 1.5 for different values. Theta is 90 degrees, the welds are in pure tension, and so we get the full tensile strength. 1.5 times 2/3 of XU is XU. When theta is 0, we get just 0.67 PWAWXU, and we could get anything in between for different potential segments of weld. Okay, so we just talked a little bit about the strength of welds in pure shear, how that might change when welds are loaded in pure tension, and a factor we might have to account for the different orientations of the weld to the applied force. Does anyone have any questions about that before we continue on? Yeah.
When do we use this factor? Can you give like an example of a situation where we would use?
I'm about to. I'll show you when. Before I do that, though, I will also say, or maybe I should, yeah, I'll say this. One of the things that happens here, generally speaking, well, we would use it, maybe I'll get straight to the point here for a second. We would use it whenever we have welds. So these welds, for example, right, we've got 2 that are loaded in pure shear, and maybe we have a third weld here that's loaded in pure tension. So when we're calculating the strength of the 2 red welds, theta is 0, and we would use this equation to figure out, well, we get a factor of 1, and so we wouldn't use the equation. When we're dealing with this size, over here, theta is equal to 0, and so when we're calculating the strength of that weld, we would use the factor for theta is equal to 90, and we'd get a factor of 1.5 strength of that weld. So it generally depends on the angle of the weld to the applied load. The applied is generally not going to change. It's going to be a tension or compression force, and so almost always theta is 0 or theta is 90. So is there when I should have written 90. It's it's uncommon that theta is anything else, but it might be from time to time. Now, when we're looking at welds with different orientations, as I've alluded to so far, we've perhaps here, maybe we have 2 welds that are loaded at theta is equal to 90 degrees. The red welds here are in pure shear, the blue welds in pure tension. The problem is we can't just calculate the strength of the red welds, calculate the strength of the blue weld, and add them together. Does anybody see from this graph why we can't do that? Well, if we have the welds in shear and we have the welds in tension, and we're pulling the connection apart, and generally speaking, the deformation rate is going to be about the same. We're basically going to be stretching the welds more or less the same at each point in time. And so by the time we get to a strain over here, let's just say the deformation millimeters per millimeter, whatever that means, at that point, we've reached the strength of the blue weld, right? The blue weld is loaded in direct tension. I should be using blue there, so I'm not confusing things, I guess. Up here, we've reached the ultimate tensile strength of the blue weld, so that weld is not going to carry any more load anymore, and in fact, the load's just going to start to drop. What is the strength or the stress that's developed in the red welds? at the same time. The strength in the red welds is somewhere down here, maybe only 80 or 85% of its ultimate tensile strength. So because welds and shear are more ductile, the behavior of steel and shear is more ductile, we're not going to achieve the ultimate strength of the shear at the same time we achieve the ultimate strength of the welds loaded in direct tension. What that means is we need to reduce the strength of the red welds to account for this strain compatibility problem. The simplest thing we do is we follow the guidance in S16, and it says when we have multiple orientations of weld, the one that has the largest angle relative to the applied force, that segment is going to have its strength reduced using a factor of 0.85. What does that mean here for us? Well, this is a pretty common situation. You'd have welds in shear on a couple of the sides and then the end of the member welded with a weld that will be in direct tension. When we're calculating the strength of the blue weld here, we're using 0.67 phi AWXU multiplied by the factor to account for here that theta is equal to 90 degrees. And the factor for that weld is just taken as 1. And so we have this weld strength multiplication factor. In this case, we have theta, I just want to make sure it's given 1 for 1. Segment of weld that has the largest angle. And so here we take the full strength of the loaded in direct shear equal to 90. And for all other ones where the angle is closest to 0, we're going to take the 0.67 phi AWXU, which is also multiplied technically by this 1 plus whatever factor, but we know for welds in direct shear that's 1. And in addition to that, we have to reduce the strength by 15% for that weld to account for the fact that the stresses are not going to build up the same way in those welds as they do on the weld that's loaded in tension. Okay, so we talked a little bit about different weld orientations, how that changes the strength, and it's not uncommon to have welds in multiple segments that might have different orientations. When we have orientations, we'll get the full strength of some of them, the ones where theta is closest to 90 degrees. And for other welds, we don't get the full strength. We have to include a slight reduction on those other welds. Does anyone have any questions about that before we get into an example of how this might be applied? Okay. The one last thing I'll say to the example is that this is very similar. It might sound similar to block behavior. When we were dealing with the strength of the shear faces, when we talked about block shear for bolted connections, we didn't use FU either here, right? We used Fy plus Fu over 2 to account for the fact that the stresses do not build up as quickly as the stresses on the tension faces, and that's basically the same thing that we're accounting for here, except we're using an MW factor that's 0.85 instead of averaging any kind of strengths in the weld. So we're going to go back to this example building because we looked at the bolted connection here before, right? Where we already looked at the one at the upper right-hand side here. We calculated the strength of this bolted connection, and now we're going to come down here and calculate the strength of the welded connection. So here we've got a flat bar, and I've just made up these weld sizes just to reinforce the concepts we talked about this morning. So we've got the same bar, pardon me, we have the same bar, same load, just the other noted by the weld symbol shown here connecting the bar to the gusset plate. What does weld symbols mean? That's an important thing. Yeah, exactly. So let's deal with this one first. 6 millimeter weld, this side of the arrow, right? So we're going to have a 6 millimeter fillet weld. There's no length given there. That implies weld the full width. So that's one of them. What does the other weld symbol mean? So we've got a 200 millimeter long weld on both sides. Great. Okay, so weld symbol here means that on this 6 millimeter weld, millimeters worth of weld on both sides of the plate. Okay, so our goal here is to determine whether the welds shown here are adequate to resist the factor tension force of 580 kilonewtons. Does anyone have any questions about what we're trying to do here before we get into the calculations? All right. What do we do? How many weld segments? Sorry? There are 3 weld segments, right? 1, 2, and 3. Orientations do we have? What are the weld orientations? For the red welds, what's theta? 0 degrees. They're loaded in direct shear. And for the blue weld? Theta is 90 degrees. Great. So we have 2 weld orientations across 3 segments. We're going to group segments 1 and 2 together because they have the same angle. We'll calculate the total length of weld for those segments, calculate the strength. We'll calculate the strength of the blue segment on its own, accounting for the fact that it is, and then we'll combine them in a way that makes sense based on the strain compatibility. Okay, so we're going to start with the here first. For the red welds, the length of weld is how much? The total length, yep. It's 400. So we've got 200 one side, 200 on the other side. The total length of red weld is 400 millimeters. The area of the weld is d over root 2 LW. The size of the weld is 6 millimeters. That's by root 2 because we're not given the throat dimension, we're given the leg length. Times 400 millimeters. We get an area of weld for the welds loaded in direct shear of 1,697 millimeters squared. Question? Calculation. We'll calculate the strength of the weld on its own. We have 0.67 phi W AW XU. Do we need to multiply it by the factor 1 plus sine of theta to the power of 1.5 here? It's 1, right? So technically, sure, we could load it, but we know it's in direct shear, and S16 gives us the strength of welds in direct shear without the factor. So we'll have 0.67. Don't confuse that with the resistance factor, which is also 0.67, 1697 millimeters squared, 490 MPa. I guess I didn't denote these are E49XX weld, but we get 490 megapascals. The strength of this weld all by itself is 373 kilonewtons. Any questions about that calculation or what that means before we go to the next segment? So that's the strength of these red welds, all on their own, as if the other weld wasn't present. And if we didn't have a blue weld there, the strength of the connection would be 373 kilonewtons. However, we do have a blue weld here, or at least the one that I've colored here in blue. And so we'll calculate the strength of this particular one. LW for the blue welds. What's LW for the blue welds? 150, right? Because it says here the flat bar is 150 millimeters wide, and we're welding the whole edge. And so LW is 150 millimeters. AW is D over square root of 2 LW, which is 6 millimeters over square root of 2 times 150 millimeters. That gives us an area of weld for the blue segment of 636 millimeters squared. The strength of that weld on its own VW, AW, XU. Here the angle is not 0 degrees. They're not loaded in direct shear. And so we have to multiply it by the 1 plus 0.5 sine of theta to the power of 1.5. So that gives us 0.67 times 0.67 times 636 millimeters squared times 490 MPa. And we can plug 90 in here. That makes sine theta of 1. This whole factor is going to be 1.5. And so I'll just simply write 1.5 in the brackets there. The strength of that weld, all on its own, is 210 kilonewtons. All right? Any questions about that number or what it means before we continue? Now my screen's not updating, which is great, but we had the, well, what the hell am I supposed to do with this here now? Well, that's frustrating. Anyway, maybe I'll just write on the board here quick because, well, why not? Network interrupted, fantastic. Okay, so these two welds here, the total strength was 373. This weld over here, the total strength was 210. The total factored force acting on this connection, 580 kilonewtons. That sounds pretty good. 210 plus 373 is 583. That should be fine. Does that work? Why not? We have to multiply one of those by 0.85. Does anyone remember which of those we need to multiply by 0.85? So it's not the 210. The other one, right? We need to multiply the welds that had the smallest angle by a factor of 0.85 when we're combining these together. So basically, the total strength of the welds is going to be 0.85 times the 373 kilonewtons plus 210 kilonewtons. So the total strength of those two welds when they're working together is unfortunately just 527 kilonewtons, which is less than 580 kilonewtons, which is not good. Okay. Does anyone have any questions about why we can't just add these two strengths together and why we have to combine them this way in calculating the total strength of the connection? So thankfully, that's not the actual detail in that building. I made that one up. And the actual detail is something that is more like this. They actually have 8 at, what did I say here, 250 on both sides, okay? So the real detail is two welds loaded in direct shear, and so we've got 8 millimeters here, 8 millimeters here, and 250 millimeters worth of weld length on either side. And we could quickly do some of those calculations just to see what that looks like. LW is 2 times 250 here, which is 500. AW is D over root 2 LW, which is 8 over root 2 times 500, which is 2,828 millimeters squared. And if we plug that into the expression for shear resistance, 0.67 VW AW XU, we get 0.67 times 0.67 times 28, 28 millimeters squared times 490 MPa, And if we were to actually do the calculations there, we end up with 622 kilonewtons. And if those welds are the only ones present, we no longer have this weld here on the end of the plate. Do we need to reduce that weld strength at all? By the 0.87 we reduced the longitudinal weld strength by last time. No, the only reason we needed to reduce the strength of this weld was because this one was going to fail first. And so to account for the fact that that one's failing first, we had to reduce the strength. These are all by themselves. There's nothing else we need to account for here in this connection. And so the real detail in our case ends up working. We have 580 kilonewtons of applied force, 622 kilonewtons of resistance. And so the real detail there worked. I just wanted to show you something that was a bit more interesting and a bit more involved because this calculation was perhaps a little bit too simple for the stuff we talked about today. Okay, does anyone have any questions about the example, either the first orientation of the welds that we talked about or the second before we wrap things up for the morning? Okay, well now you should be able to determine maximum, minimum fillet weld size requirements. They're tabulated for you. Calculate the strength of fillet weld segments, connecting a tension member to a competent gusset plate, and consider the influence of different weld orientations on the strength of the different weld segments that we might have connecting the brace to the gusset plate. Does anybody have any questions about anything we talked about before closing lecture this morning? Cool. Have a good weekend, everyone. We'll see you on Monday.